For the rest of the talks, the data is rarely complete, and so the plan today is to talk a little bit about some studies I've done with Jeff Smith and John Morgan on thinking about when missing data matters and how it matters and what you might be able to do about it. So that's the big picture issue. I will go a little bit fast just because we are a bit behind on our schedule, so I'll try to make up a little bit of that time, which is probably frightening because he already speaks fast, but we'll see where we end up with there. The work today is building on a series of 3 papers that John and Jeff and I wrote. It was one of my life goals to get papers with no Roman numerals in the title, so we managed to pull that off, and so there you go. The advantage of that is you get to dig deep into something and really sort of explicate the way that it's the process works. The cost of that is that it's a lot of detail, and I don't know if we're actually going to go through all that detail. So. Let's first make sure we understand what we're thinking about. So network data are often incomplete, and the notion of incomplete data is built around this idea that you know that there's a boundary specification, even in the best case. So not when you have a closed population, so like you really only care about kids in a particular preschool or adolescents in a high school, you probably get some set of kids who don't respond. So in this little diagram here, we have the entire population in the way the real world should be if you could actually measure it. And then what you have are a series of people in red who just didn't respond to your survey, right? So that you know that there's missing data there. And so what you observe is a subset of the data. And that's the thing you have in your hand. And what you want to do is infer about this critter from the information you have in this critter. That's the goal of the process. And what we wanted to do was figure out, well, what happens when you're faced with this problem? What's the actual damage that this kind of thing does? In particular, since the vast majority of researchers, quite frankly, just walk out the door with this and treat it as if. And so how much damage are you doing if you do that? How much damage are you doing to the descriptive statistics? How much are you doing to the inferential statistics and so forth? And so our plan was to figure that out. And we can think a little bit theoretically about how this works. And so if we know what a true network looks like, we can imagine what people might write down on the survey. So in this case, we know that the true network, we have ego, they've nominated a set of male and female friends. Some of them are identified and some of them are not. The problem with a lot of our instruments, and this is built off the EdHealth model, is that all we know is that this male nominated a person outside the school, for example, and this person did as well. We don't know that that's the same person. So there's lots of ways that data can get distorted, even when you collect some information about the kind of missing data you might have. And there's lots of different ways that this can look like. If you have a case where the ego, the person that you really care about, just happened to not make it on your school roster, which happened a lot in EdHealth because we had to print the rosters in the spring and administer the survey in the fall, right? So you end up with people who show up, moved into the school that day, they fill out a survey, and all of the rest of these people nominate him as a friend, but we don't know that that person is in the data set, right? So there's lots of ways that data collection can go wrong. Thankfully, new data sets can get a little bit better at that. Some of the new, something like Network Canvas, for example, you might be able to give yourself attributes and names and so forth. One trick that I recommend is to think about to use the old the political trope, the known knowns and the known unknowns and the unknown unknowns, right? You have this kind of a model that you can think about the data you know and the data you don't. And so when you have data where you have some kind of a boundary built around your data set, where you know that the connections are within and between, you can actually figure out that you have contacts amongst the people in one set and any non-contacts among those people. So if I have for a focal actor and they've nominated some people and they didn't nominate those people, those zeros are meaningful zeros, right? So those are actually informative. So the real no is a no in that case. What we don't know is about the people on the outside. And depending on your design, like the kinds of relations in this set where the people are on the outside and you have no way of interacting with them or knowing what they're doing is what's going to drive the outcome. And there's lots of different ways you can do this. So you might have a link tracing design, for example, and in link tracing designs, you might not collect data amongst the alters at a given wave, and so that creates new ways. But I just want to point this out, that this kind of a rubric where you can sit down and sketch out the adjacency matrix and ask yourself, who do I actually know all the relations, who are at risk in my survey, is a good way, or in whatever data collection mode I have, is a good way to figure out what your known and unknowns are. So there's a couple of different scenarios. So what we did is, so that's the question, I just repeated it. What we did is we took this as a simulation problem. And so this is a classic Monte Carlo design. We generated the truth, and then we messed up the truth, and then we re-estimated our measures of interest, and then asked, how does that compare with the true measure of interest? And that's really what all of these studies have done to various and different degrees. And the final study is applying an imputation strategy once we've done this, and I'm going to talk through each of these in a little bit more detail. I'm a big fan of dealing with data that looks like the kind of data that people actually play with. A lot of Monte Carlo designs and a lot of statistical modeling sort of building tools deals with random networks, and the problem is most of us don't deal with random networks. Those networks are not realistic, and a lot of the properties of random networks don't apply to the data that we actually care about. And so I take the other extreme. I grab a bunch of real data and then mess with that. And the problem with that is that what you give up is a certain amount of formal generalizability. So these data sets, these 12 data sets that we're going to play with, are unique, and they're sort of they're idiosyncratic in all the ways that any 12 data sets would be. But we chose them deliberately, so we had a chance to choose from amongst a lot. And so the 12 we chose ranged in size from the smallest is 43 nodes, the largest is about 1,000. They're undirected and directed networks. They cross lots of different substantive organizations. And importantly for us, they differ in a lot of the characteristics that we care about. So they differ in whether they're directed or undirected, whether they're centralized or not centralized, whether they are really dense or really sparse, and so forth. And so we have a lot of these different styles of networks that we can then use to think about how those characteristics of the network, so of the true network, affects the imputation and the understanding of the kind of missing data you have. And so these are the 12 networks that are in there, kind of pretty pictures. And so once we do this, so just to remind us what we're going to do, we're going to take one of these true networks, so we're going to take the Colorado Springs HIV network as we've observed it, and we're going to treat it as if it is true. And then we're going to say that's the true gold standard. We're going to go in, and I'm going to pick at random some number of these nodes, and I'm going to delete them. And I'm going to either delete them purely at random or at a bias random. So I might delete peripheral nodes or central nodes, for example. So there's a different set of scenarios we have. And then I'm going to recalculate a bunch of statistics. Well, what kind of statistics are we going to calculate? We're going to recalculate the kind of statistics that investigators will use. And so we're going to talk first about a whole series of centrality and centralization scores. I'm not going to talk much about centralization today. Centralization is a complicated measure, and so it's just not worth the trouble today. But if you're interested, I can go back to it. But centrality is a node-level feature, and it ends up being a little bit complicated, and I'll explain why in a minute. But we calculate a whole series of centrality scores and a whole series of topology scores. At the topology level, we're dealing with sort of the basic structure of the network. So these are the things about reachability I talked about yesterday, as well as some common standard metrics that you might calculate at the graph level, including the transitivity ratio or the clustering coefficient, the extent to which the network fits a ranked structure hierarchy, to build on some of the work that Craig was talking about a minute ago, and whether or not you can replicate a Concord block model put on these models. So that's just a sense of what that is. All right, so when you do this, what you want to do is calculate a bias score. You want to say whether I have the true measure and I have the new constructed measure once I mess up the data, how much do those match? But the problem is I have, if a network of 1,000 nodes, I have 1,000 scores I have to compare in order to have the true to the real to see which one get messed up. And that's just cumbersome, right? So we needed a way to summarize the bias in the individual scores at the network level. And so what we came up with was this idea of treating for individual level scores to treat the bias as the correlation with the observed true score. And so in this case, for example, you can know that this is the true in degree in this particular network. And then if we delete nodes with 10% missing data up to 70% missing data, we can fit a new line to the in degree that people get, and we can see what the correlation is between the true score and the observed score. Now, obviously, with in degree, right, so that's the number of ties you receive, if I delete 70% of the nodes, the actual in degree score is going to be much lower. And so the actual score here is the in degree in this case true in degree should have been about 75, and the actual in degree is about 30. But what you're really interested in most of the time when you're dealing with individual level scores is you're going to plug those into a general linear model of some sort. And so what you really care is that the proxy for the truth that you have correlates highly with the actual true score or not. So that's why we chose this measure. And so in order to summarize this pattern, we have this sort of piece at the end. And so what this tells you is how much missing data we're introducing to the network, and what's the observed correlation with the true score. So in degree is actually an interesting case, because when you have up to 70% missing data in this particular data set, you still end up with a mean correlation of above 0.8, right? So your correlation is really pretty good on in degree when you end up with there. And the range, depending on, because we do this 1,000 times for each scenario, or 100, I don't remember how many times you do now, a bunch of times. Yeah, go see the details in the paper. So we do it a bunch of times for each scenario, and so we get a mean, an interquartile range, and a 90% range. So the reason I spent all this time talking about this particular setup is that I don't believe in doing simple things, right? And so the kind of complexity you get, it turns out, is a different pattern. The true network structure really matters for the kind of pattern you're going to observe due to missing data. And so the big picture story here, if you take nothing away from this talk today, is that the effect of missing data on your true score depends on the structure of your true score. So if you don't have any good intuition about what your true network looks like, then it's going to be really hard to fix it. And so what we spent a lot of time doing over the course of these 3 papers is trying to figure out what the systematic features are of those networks so that we can help inform what people do. And so let me walk you through this a little bit. We arranged the columns here of these 12 networks by size, so the smallest network to the largest network. The shaded columns are directed networks. The unshaded are undirected networks. And you can kind of see the general pattern. If there is a general pattern for these centrality scores, it's that, as you might expect, the greater the missing data in any given network, the more bias you're going to see, so that the lower the correlation with the true score. Now, it really matters in your small networks. So if you have networks of less than 100 nodes and you delete 70% of the cases, you don't have a lot of information left that you're trying to fill in. And so you're going to end up getting a pretty poor fit. The extent to which that fit is more or less poor is fit by this slope coefficient, and you can read the paper to get that, but you can kind of see where this is at. The one thing that's really, I think, interesting about these scores, and I think I might have this here, is that the volume scores are actually pretty robust. So volume scores are in degree, out degree, and total degree. And so if you have a relatively large network, so over a couple hundred nodes or so, most of these scores you'll notice that the slope, the range is narrow and the slope is pretty flat. And so you end up with very little missing. So you can do a pretty good job, even if you have significant missing data. We're talking 70% out here at the end. You're still getting correlations in the 0.6, 0.7 range. Now, if you've ever done a psychometric score and you get 2 items that correlate at 0.6 or 0.7 on your index, you're pleased as punch, right? That's fantastic. So actually, from a data quality standpoint, you do a pretty good job on volume. So if you're interested in popularity or if you're interested in degree, missing data doesn't matter if the data is collected, if the data is missing at random. So this graph is data missing at random. For the kind of centrality scores that deal with path structure, it's a lot more complicated and a lot more finicky. What you end up with is much higher levels of bias at the heavy missing data rate, and some really weird patterns depending on the kind of data you have. In general, probably the most finicky measure by far is the betweenness score. So betweenness centrality is very sensitive to missing data, even if that data is at best collected perfectly at random, right? So if your data is missing perfectly at random, even then a fairly small amount of missing data, we're talking like 10 to 30%, is going to lead to pretty significant bias. Monocyte centrality, your eigenvector measures, are amongst the most stable of the centrality scores of these path-based measures. And that's in part because they're building on the degree centrality scores, which themselves are stable. So those do okay in the sense that you end up with scores that are in the 0.6, 0.7 range, even when you have 50% missing data. And then closeness centrality kind of falls between. The reason you see these little funky curves here is that at some point the distance matrix gets so destroyed that you're essentially not getting any change in the path structure once you get that much missing data. Now again, this is a severe missing data. If you're missing 50% of your cases, you might want to ask yourself what you're doing anyway. But we wanted to push this model as much as we could. The other set of scores we started to deal with is a lot of the reason, especially in the networks and health field, is that people are interested in collecting network data because we care if there's a peer influence process, if there's a network autocorrelation. And so we simulated a network autocorrelation function in all of these networks and then asked, could we recover that network autocorrelation score? And there are two versions of homophily then that we test. One is degree-based homophily. Do I have the squares there? And so that's assortativity or disassortativity. And the other is a behavior-based. And the story here isn't that you end up with bias. The good news from both of these stories is your statistics end up being unbiased, but they become really uncertain. And so the variance in these things sometimes just goes off the scale, right? So if you have a really large network and you have data missing at random, you're in good shape for any of your homophily scores. If you have small networks, then it goes to shit quickly. But I think this is a really important point that people are, and I just want to re-say it again, is that network autocorrelation is a stable statistic in the face of missing data. In the face of if you can arguably assume that your data is missing at random, you're in really good shape doing a network autocorrelation model. Right, even if your centrality scores could be screwed up, but your network autocorrelation model is in good shape. And so that's something I think that is a finding from this study that's a little bit underappreciated, that I think is good news for those of us that are out there doing the work collecting data and might not have all the data we wish we had. The topology scores are also, by and large, fairly stable, especially the sort of individual level kind of scores. So these transitivity ratios, these clustering coefficients, and we don't have it here, but there it is, the Concord score. Those do really well. The size scores, I mean, as you might imagine, your ability to recover size when you're missing a bunch of data is going to be wrong. So that ends up going away. So that's what that is. As you can tell, this was a pain in the butt, right? So there's all these different kinds of results you could get. And so we wanted a way to help people figure out sort of what a summary might be. And so we generated a series of tables in the paper that are effectively meant to be, for those of you that are old enough to remember this, the kind of statistical lookup tables that'd be in the back of a stats book, right? And you'd say, I have this sort of series of combinations. This is where my case falls. And that's what this is. So if I have a network that looks like one of these, so I'm dealing with something that, say, one of the Prosper schools or a smallish ad health school, and I've selected my data such that I remove peripheral nodes, which is I'm selecting them randomly but negatively correlated with centrality. So I'm removing peripheral nodes. I can lose up to a third of my sample and still have a 90% correlation with the true score. Right? So that's the way you read this table. And if I'm selecting, so in a lot of these cases out here, for example, what this is telling me is that if I'm removing this score, I could remove up to 70% of the cases and still have a correlation that's greater than 0.9. So this is exactly what this table is meant to do. So you're meant to sort of think, well, what kind of data do I have? Which was the sort of closest approximate to the data I have in hand? Let me go to this table and see which of these scores is going to match well. Right? And you can do it again for your other kinds of scores. The topology scores has the same kind of feature. Again, what I think is really nice about both of these is the takeaway story for these kinds of data, even when we have directional missing. So this is non-random missing. This is biased missing, either peripheral or central. You can be missing on average, close to half of your nodes for some of these scores and still get a reasonably good score. Right. So that's the piece there. The scores drop a little bit when you start dealing with some of the homophily scores and you're dealing with bias, right? So the degree homophily in particular, if you can really only afford to miss about 20% of your data in order to get a good or a reasonably approximate score with assortativity or disassortativity. But again, if you're dealing with behavioral homophily, you can lose up to 50% of your data and still be in reasonably good shape. So it's a bit of a heretical statement, just to reinforce what I'm saying here, is that a lot of missing data doesn't necessarily mean your study's invalid because, under at least these kinds of assumptions, the data works out pretty well. That said, if you have missing data and you have some kind of an idea of why your data is missing, it might be good to try to reconstruct that data. And I think that many of us are in the situation where we're asked to reconstruct the data and to impute this missing data. And what's a smart way to do it? So what we decided to do in this final version of the paper is work through a set of common imputation strategies. And so the baseline strategy here is what everyone does in practice, which is do nothing. So just take the data as given. It's listwise deletion. I got it off the UCINet dataset page, or I got it out of IDNet, and there it is. I'm just going to live with it. But we know that that's we can do this perhaps a little, or we think we might be able to do a little better than that. So what are some of the options? So one of the options is to, so just to be clear, we're assuming here that the missing nodes that aren't sampled are uniquely identifiable, which is a big assumption of this work, but that's the scope conditions of the work we're doing. So we know that Billy's in class, he's part of this classroom, but he didn't fill out the survey this day, right? And so that node is missing. And what that means then is we can say that we know that A and D nominated node E, and we both know that they nominated the same node E. So that's our assumption of this model. And so the simple imputation model is an asymmetric model that says we just add back in these ties from our surveyed nodes. And so if you've collected data on all your surveyed nodes, you keep every edge that they've told you about, even if those people they've nominated can't respond to you. Now what this means is that necessarily some of your scores like reciprocity are going to be messed up because we're not giving the other people any opportunity to answer back, right? But we're just going to close our eyes to those kinds of constraints and just ask what happens. The other is to say, let's assume sort of the opposite of that, which is that if ego nominates someone who's missing, let's assume automatically that they reciprocate. So we're going to treat that as an absolute reciprocation rule, that if A nominates B, B nominates A. And then both of those are probably silly. The more likely thing that people are going to do is say, well, with some rate, let's put that reciprocal tie back in. So the out ties are true. We know that ego nominated alter. And then the probability that alter reciprocated that tie is equal to the probability of reciprocation in the network at large. And so we just take that and flip a coin. You might do that because it's a random imputation idea. You might do that 100 times or a few times and then recalculate your score and take the average, that kind of thing. Now, then all three of these we call sort of simple models in the sense that you can do them without really any other kind of manipulation than maybe a for loop, right? That's as complicated as it gets. The other model we refer to is, or the other way of imputing data that we focus on is model-based imputation. And here what you do is you statistically model the pattern of ties in the network, and you apply that model to your out-of-sample cases. Right? And it turns out, the good news is, from even since the time that we wrote this paper, this is now really easy to do. So the ergom package and the StatNet package in particular now make it possible to just add the NAs into the data set, and it'll just automatically do this for you. So so really, like it used to be that this kind of modeling was the simplest thing to do. Now if you're doing any of this, it really is pretty straightforward to do that. All right. So we fit two kinds of models to the data. We set a very simple model, which is just the density and some homophily terms, and a slightly more complex model, which just says a density, some homophily terms, two homophily, I forgot my two there, and a closed triad term. So that's so a little bit of local clustering. Now, obviously, what you would really do is you would tailor your model to whatever is the best thing for whatever kind of data you're dealing with. We didn't do that. We wanted to use the same model across all 12 data sets. But we cheated, and we made up the homophily terms so that they're really good homophily terms, okay? So the kind of homophily term we're using is effectively a distance in a latent space. So it really is a pretty good predictor of where you're at. Excuse me. So what should you do? Again, there's no simple answers. It depends on the kind of network you have and the kind of measure you're trying to do. So the summary of the best imputation models for any centrality measure is going to be, depending on whether or not your network is directed or indirected, the kind of response type you have, so that whether or not you're dealing with central nodes being removed or less central nodes, for example, and then this tells you what the best response category is. The good news is that most of these strategies actually work pretty well. And so, for example, if you're interested in degree, for any kind of missing on an undirected network, any of the strategies except listwise deletion is going to be better than nothing. So just do something. That's the rule, right? So if you just do a little bit, you're going to help a lot. And the only sort of ones that really get to where you need to do something important is if you're dealing with some of the path-based measures and you're removing central nodes, so central nodes didn't respond to your survey, for example, then you're going to want to get into some of the more model-based things. And again, you're seeing that here when you get into the projects that are the kinds of missingness that's generated on directed networks. If you're dealing with the scores that ends up being like closeness, then the model-based matters. Now, what am I basing these recommendations on? We went through and we averaged, we did a bunch of these models, and we compared the bias you would expect to see out of each of these kinds of settings. And this sort of quantifies that bias for you a little bit. The black line on the top is the bias you would have observed had you done nothing, and then this is the bias you would observe if you did one of these other models. And this is data missing at random, removing peripheral nodes, removing central nodes. And you can see that the model-based corrections, or sorry, any of the corrections for dealing with the removal of central nodes are going to do better than you would do if doing nothing. But in many cases, there's really no discernible difference between doing a complex model and doing just a simple symmetricizing, right? So some very simple projects can actually make your data a lot better. And intuitively, the reason for this appears to be that effectively a lot of what happens in missing data is a screwing up with the denominator of these kinds of measures. And so by just putting the nodes back in and giving them some semblance of ties, you're effectively correcting the denominator of these scores, and that makes the thing work better. Now you can do that more or less smart, and so there is, if you were to zoom in, you see a little bit of a difference between the model-based versus the simple sets, but by and large, doing something is better than doing nothing, and doing something simple is often good enough. That's also true in the directed networks, and the directed networks do a little bit better. You find a little bit more power from using either the model-based approach, which is this orange one, or sometimes the what do you call it, just the simple probabilistic one. The very simple symmetric and asymmetric models don't work quite as well for some of those. Now, interestingly, as you might imagine, the bias is almost always the largest when you're removing central nodes. When you're removing peripheral nodes, or removing data at random, it doesn't really matter that much. So it tends to be, and the obvious reason for that is that the central nodes are carrying the most of the volume. And this is another one of those. So again, another one of these models that sort of walks you through what are the things you can do and what should you do if you get there. A whole series of these different decision trees. Like I said before, it's always frustrating as a user to say that the answer is it depends on what your data looks like. So what we ended up doing, I'll just, in the interest of time, just jump over to this set as well, as we've provided in the paper a series of decision trees to help you as the user figure out what your best option is. So if you're dealing with a very centralized network and you care about topology measures such as transitivity, then you at least want to do the asymmetric imputation. And given that the other two measures in the topology set are best done with probabilistic, then maybe you might want to bump up to that. Just a little bit more complicated. And so we have these kinds of decision trees built for each and every kind of model in our network. And so you can do for centralization measures, centrality scores, and the different kinds of imputation that go through there. If you have a different kind of metrics, you get a different kind of outcome. And undirected networks, the same thing. And so that kind of variance in the best fitting thing is what we're trying to capture with these sets. Now, you might say, Christ, Moody, I'm not going to go look up your paper. I love you and all, but I'm not going to go look up your paper every time I need to figure out what to do with my data. Alas, you don't have to. We have a tool that is built that it lets you figure out what kind of data you have, the kind of score you're interested in doing, the number of nodes in your network, and a series of other parameters, and then you can say, what kind of bias am I going to get? And so in this particular case, you can say that if I'm interested in a network that looks like a co-authorship network, and I'm interested in pulling out nodes, I assume that my data is not missing at random, but it's associated with the closeness centrality of my nodes, then I can figure out how big my network is, whether it's not it's directed, and then I can figure out what the resulting bias might be. And this says that in degree is only biased by about less than 1/10 of 1%, and the most bias is going to come, it looks like, between the centrality is biased by about 6%, right? Now, this calculator comes with a big asterisk, which is that we wrote it in Java, in the last version of Java, so it's currently broke. All right, so this is the worst car salesman ever, but there you go. So that's what happens. And so the good news is that this is on the list to be added to IdeaNet, and so this will be just another tab on the IdeaNet visualizer, and we're going to have it built into R, which is, backwards compatibility is not R's biggest thing, but apparently it's better than Java. So that's where we're at with that. So this is the kind of thing you can do. I think the big picture story that I want to, oh, there we are. The big picture story I want to say with missing data, again, is that you're going to have missing data. And one of the things that I sort of hope that people get from this series of papers is that when we simulate the missing data, we simulate it all the way out to 70%. And so you get a huge amount of missing data. If you have a reasonable sample and a reasonable survey, and you're dealing with something like 20 or 30% missing data, which already seems high, you're probably fine. And so I think one of the things that you can sort of rest assured is that a lot of the kinds of sensitivities that we're worried about in network measures came from some really early studies in the 70s and 80s that was using networks of 30 and 40 nodes. And for those kinds of, if your networks have 30 or 40 nodes in it, you have to be really careful. But there is a law of large numbers effect. If you end up with relatively big networks or a small network calculated over a lot of different iterations, if you have real-time data like Craig has or other kinds of small networks that you've collected many replicants of, then those kinds of things, the errors essentially average out. And so the missing data problem isn't as damning to network studies as we might have originally thought it was. And I will stop there, and that'll get us roughly close to back on time. All right, thank you. Questions, comments, thoughts, concerns? Please.
I highly doubt this is possible, but sometimes so I do a lot of ego network data collection, and one of the biggest problems I run into is the teeny tiny network size. And sometimes people might not include all the culture tie questions, and so you're super limited on the information that you do have about the network. Depending on the network, so for instance, like if you're assisting college students and their ego networks, could you do something maybe similar to this, where you're like, well, it's within a school, I don't have sociocentric measures, but based on maybe how many alters they have listed versus not listed, like I can kind of infer maybe what that network would look like. I know we can extract ego networks from sociocentric networks, but I highly doubt you can go the other way, so you can't really create information. But I'm just kind of trying to think of how
yes, you can. So I think one of the things there's two versions of this question. So I think the question is, what can you do if you have ego networks and perhaps missing data on the sociocentric data from the ego networks, and you'd like to know the alter ties that are built into this. And so if you have essentially two types of data, and the alter ties are missing from respondents, but they're in the survey, so you have some people that have them and some that don't, then you can infer cross from that. If it's a design issue and nobody has alter ties, then what you can still do is take the mixing matrix from egos to alters, and so you know the number of times that a person of type X nominated a friend of type Y, and then you can say of your alters, the likelihood that a person of alter of X nominates an alter of Y is going to equal the mean of the number of times that respondents of type X nominated alters of type Y. And so you can take the same information because essentially what an ego network survey is a sample of edges. And so what you have is a whole sample of edges, and a pretty good sample of edges probably often, because you probably had some kind of sampling design other than picking a kid in the hallway that just happened to have big ears that you grabbed on the way by, right? So if you have some kind of a sampling design that says this is some probabilistic set, then your sample of edges is also a probabilistic set, and so you can infer from that sample of edges to the edges you didn't observe. And that's a nice thing to be able to do. Now, what you might like to know is some features that aren't attribute mixing, and that's going to be a lot harder. So you're not going to, especially if an ego network design is built around a limited set of alters, like 3 or something, you're going to have a lot harder time saying who's really popular or who's not. Now, if you were lucky and you did this kind of study in a school, and you have any kind of minimal identifying information, then you have an in-degree sample on the alter. So if you know the alter's name, then that's great, because now you get an in-degree distribution, because the same alter will get nominated multiple times. And that in-degree distribution would at least get you a bit further by inferring a total network. So we will talk a bit about this on Thursday when we talk about simulating networks from models, and that'll be part of that set. Does that answer the question?
Yeah.
Please.
I have a question about network size. For example, my data set, I have average 15 students in one class, but I have 20 classes, so the whole students are about 300. But I just measured that the interaction within the class, there's no interaction between the classes. So in this case, would you say this is a small network or is it big?
So just to repeat the question, she has classrooms of like 15 students. You have 30 some odd of those replications, which would give you 30 times 15 is like 300 or 400. And my math arithmetic skills online are far quicker, slow, but on that kind of order of magnitude. And the full sample in the school is something like 3,000. So you have about a 10% sample of the total school in these different classrooms. And are 15 students in the classroom the size of a classroom? Yeah. So you have replicates of complete networks within each classroom. So in that case, you really have a nice sample of networks. And so you have, effectively what you can do is you say, I have a boundary condition about within classroom interactions. Those within classroom interactions are fully observed, and so your zeros are meaningful zeros. And you can actually pool those networks and estimate the models simultaneously. So one of the nice things about the new ergo models, for example, is that you can take all 30 of those schools, put them in one giant adjacency matrix that is block diagonal, and say, fit a model using the cross-classroom information, not linkages of nominations across that, but in the same way you do a classic HLM, you're borrowing some of the variance from within schools to apply to a mean across schools. And that's really a nice way to do that. So I think, in fact, this is a really nice thing because from a data collection standpoint, it's much more efficient to have 30 replicates than to do every classroom at the school. And you have the power now with this kind of multiple network models to actually fit it. So I think you're in good shape. Now, whether or not, if there was something else that biased the kind of way these data were collected, that's a different story. But if the data were collected as best you can and those are accurate, then you should actually be in really good shape. Please, Gabe.
Yeah, I have a question. So in like traditional multiple imputation settings of a normal survey, some of the uncertainty that comes from making guesses about people's attributes, for example, ends up ultimately in the model that we'll be using, right? Some sort of like Rubin's rule or something like that. And so how does that come to be for relationships? So even if I'm aware of how much uncertainty I'm adding by choosing one of these combinations, how do I import that and make sure that it's being expressed in, say, like an urban model? So the question, so people would hear. So the question is, effectively in a multiple imputation, there's sampling variance and there's true variance in the underlying sort of model, the imputation model, and that's built into the estimates in a multiplication model. So you have the actual true variance that's built into the measure, and you have a variance that comes from the ignorance that's implied by the data you're missing. That's why you do multiple imputation versus not. In most cases, the multiple imputation case for regular standard off-the-shelf missing data, you assume that you're missing a fairly small proportion, so the amount of randomness that's being generated by the actual missing data is really quite small, which is why you can get away with doing 5 or 6 replicates or something in a standard multiple imputation. In our case, we haven't done that study, so I honestly don't know how many. So if you're doing, for example, the probabilistic study, we did like I said, somewhere in the order of hundreds, if not thousands. My memory's just clouded on that, but it was it took for months to run, and so we just did a bunch of them and took the observed distribution. My guess is that whatever if you look at those papers and you see the variance in those models, that's what that little R square was, and we also have another little sub V sort of bit put in there. Those things will tell you the amount of variance between the replicants of our study. So we should be able to calculate the question you're interested in, but I just haven't actually done it. My guess is that you probably don't need that many in realistic settings. So if you're missing on the order of 15, 20% of your data, then you're probably like you would for any normal variable you're missing, and it's probably like the rest of it. Most of the variance is real variance as opposed to sampling error variance. But I have to be honest and say I haven't done the studies with this stuff.
Awesome. Thank you, folks.